Good afternoon, almost good evening to the Nordic Pavilion for this very exciting side event here today called From Past DNA to Future Crops, Building Resilient Food Systems in a Changing Climate. We have a really amazing side event for you here today where we're going to be hearing from some very esteemed speakers. I'm going to introduce each speaker as they come and take the floor instead of doing everybody all at once now. One of the key themes we're going to be talking about and addressing today is that about technology, innovation, and looking to the past as well. Because in a time where we are looking for new ways to address mitigating climate change, dealing with climate change adaptation, dealing with feeding the world, nutrition insecurity, and trying to find ways to preserving biodiversity, we keep looking for lots of new solutions. We keep looking forward, innovation, technology. But there's also the opportunity to looking back at what we've done in the past. You know, the cliche, if you want to learn about the future, look to the past. And we're lucky to have somebody here today who can really help us with that. So first and foremost, I would like to invite Mr. Eske Willerslev, who is the professor of the University of Copenhagen and the University of Cambridge. He's going to be giving us a presentation of the AEGIS project. I leave it to you.
Yeah, thank you very much, and thank you very much for the opportunity to present this new project, AEGIS, which is funded by the Novo Nordisk Foundation and the Wellcome Trust. And just briefly, well, as you heard, I'm Eske Willerslev. I'm an evolutionary biologist, okay? And I'm a professor at University of Copenhagen and the University of Cambridge. And you can say my speciality is retrieving and analyzing DNA, genetic information from the past, okay? So the AEGIS project is trying to deal with two problems that are kind of related but still to some degree distinct. One is our food security, right? That is under threat because of climate change. So our crops was domesticated in a time of very stable climates relative in Earth history, and they are not capable of coping, with the climate changes that we are seeing. The other problem is biodiversity. So we are in a biodiversity crisis, right? We are losing a lot of species, and the main reason for this is the way we conduct agriculture. Okay, and if we don't address these problems, I mean, it will have very severe consequences, right? People will starve, there will be hunger, etc. And of course, there's many groups that are trying to address these questions. You can say where AEGIS is, I guess, unique, you can say, is that we are relying on the past, on the genetic information of the past. So the rationale is the following. So Earth has undergone many climate changes before. We know that, okay? Naturally, right? We have had periods in Earth history where the temperature was just as high as today, where the CO2 levels was just as high as today. And of course, nature has coped with these changes, right? I mean, this is why we are here today. This is why there's trees and so forth. Life has coped, and nothing is as efficient as coping with these things as nature itself, right? The question is, can we go and get at that information, right? How did nature cope with these things in the past and translate it into present-day crops and cropping systems, okay? And AEGIS is taking two paths, I would say. One is to explore in the past wild nature, right? Wild ecosystems. And the other one is to explore domestic ecosystems of the past, right? Because the cropping systems we have today is highly dependent on a lot of fertilizer, pesticides, water in many cases, right? But of course, in the past, we had crops, right, that didn't rely on these things. And it's just like with the human muscles, right? If you don't use them, you're losing the ability. So a lot of the crops have lost the ability to interact, you can say, with the ecosystem around it, right? But of course, before artificial fertilizer. They had to do that. So the information is there. Okay? Okay, so how can we get at this? Well, the way we are doing it is to use something we call environmental DNA. So this was a discovery that my group did back in 2003, actually, so many years ago. Namely that that you can take soil samples, both from the present but also from the past, that was deposited thousands to millions of years ago, right? And if you take that soil and you retrieve the DNA, you will retrieve all trophic levels of the ecosystem. Everything from microorganisms, bacteria, fungi, to plants and animals. Why? Well, because all living cells are shedding DNA to the surroundings. Okay, so when I'm walking here, my DNA is all over the floor, right? So we are walking on the DNA from the present, but also from the past. And this DNA contains, you can say, a blueprint of how did nature in the past adapt to previous climate changes. The question is, of course, can we read that blueprint? And secondly, can we translate that information into present-day crops and cropping systems? And it's really both. It's two ways, right? It's genetic adaptations, right? So one way nature is adapting is through genetic adaptation. You know, the species are adapting, right? It's called evolution. The other way is that the ecosystems are adapting. So what you see when you go back into the past is you see organisms together that are not found together today, right? So you see environments that are very different from today. So for example, when we take DNA out of 2 million year old sediments from northern Greenland, where the temperatures back then were 10 to 15 degrees Celsius higher than today, you see a forest, right? You see a forest and you see taxa that today is found in the Arctic region, together with taxa that today are only found in the temperate region. They don't exist today. There's no analog, right? Okay. So of course, it tells us something about which organisms can be together and actually interact together. Okay. 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 So this is the approach. Does it work? Well, I would say yes. We have only been working for 1 year. This is important to say. But what have we managed to show? Well, if we start with that site 2 million years ago from Greenland, if we want to grow, let's say, barley or something like that, further to the north, right? Because the temperature will increase, temperature will no longer be the limiting factor. But the light will be a limiting factor, right? Because, you know, the further north you go, the poorer is the light conditions for growth. It's already now an issue, right? Getting things to grow to the north. So we can go in, of course, in this forest that existed 2 million years ago and find adaptation to those light conditions that is in a warm Arctic. Because Greenland was, and the Arctic was exactly the same place as today, okay? And we have managed to actually cover most of the light pathway from this environmental DNA of the past. And we are translating it into barley, and some of the insertions are having a huge impact, okay, on the ability when you do the testings. And similar for the, you can say, the past agro systems, then we have worked with lake cores, sediment cores, right, from China, going back, 10,000 years to time of domestication, all the way up to the present. And what can we see? Well, we see, and this is exciting, I think, we see hundreds of mutations that is unknown today, unknown in rice, even though there's been sequenced a lot of rice variants, right? Unknown today, in genes we know are important. We know are super important. So the potential of getting new traits, right, is huge, right? And similarly, we can see how, because we have time, we can see that when they domesticated rice, how they changed the microbial composition in the ecosystem from a system where you can say nitrogen was lost, right, washed out, to keep it inside the system. And we can see the different stages they took to get to that, right? Which is the different from today, if you just looked at it today, you would see the same, but you don't know how to get there, right? Because you only see the end product of the process. And if you try to, let's say you take something from a forest, right, and you want to put it on a field, normally what happens in terms of microbes is they will just all die. Because it matters what is the order by which these microbes are introduced into the system, right? And by having time, you can see that, right? So I have great hopes, and you can say, what's the vision here? Well, my vision is, if you imagine, let's say, just here in Brazil, for example, right? There's a place where you are growing crops, right? And you make predictions about what will the future climate of this region be, right? And you say, okay, this is the future, what the future will look like. Then the idea is you can go back in the same region, back in time, to the best analog, right, of that time, get the adaptive traits, both in terms of microbial composition, but also genetic adaptive traits, right? And translate them into these crops that you want to deal with, okay? And hopefully that should help you. And if you imagine, you could do that for many different places, right? At the same time, okay, I'm sorry, I'm going over time here. But if you imagine, we just talked about it over there, right? If you imagine we are getting core samples from all over the world, from all kinds of time periods, right? You can go in and, for example, look, what is similar, if anything, across all deserts, right? In time and space. What adaptive traits, whether you have a cold desert, you know, as you had in the Pleistocene during the Ice Age, right, to the north, or it's a hot desert or whatever, is the traits that are similar across, you know, certain environments. It could also be in terms of certain latitudes or whatever you want, right? And then you could go and try to modify the crops accordingly, right? In order to say, okay, this is the type of environment, it's always the same, you know, this is what we need to do. So this is kind of the rationale here. Thank you.
Thank you so much, Eske. If I could ask the other attendees, Todd, Majal, and Anna, to please come up and join me up here. Stand in a line. Be careful when you walk. The floor is a little bit wobbly, so things might fall down, but give it a go.
Okay, good.
Great. So we're going to have a little panel discussion. I'm going to introduce the speakers in a moment. After that, if time permits, we're going to have some Q&A from the floor. And then we'll have His Excellency Jakob Jensen, the Minister of Food, Agriculture and Fisheries, to come and do some closing remarks. Let me just introduce first the speakers that are next to us here now. To the immediate left of Eske, we have Ms. Anna Euler, who is the Executive Director of Innovation, Negotiations and Technology Transfer at Embrapa. Is that correct?
Yes.
Great.
Thank you.
Thank you so much. To your left, you have Mr. Todd Rosenstock, who's the Science Director for Climate Action at CGIAR. And to your left, you have Marcel Bernot, who's the Senior Natural Resources Officer of FAO. Before we come to the question, something that just struck me, I was listening to this incredibly exciting project. If we go back 10 years from today, the Paris Agreement, adaptation was inserted into the Paris Agreement as a core part. But nonetheless, of those who've been following the negotiations for a long time, say the last 10 years, you've seen how adaptation has still not gotten the time and space it needs. And we're seeing now, particularly within agriculture, smallholder farmers all over the world, and large-scale farmers for that matter, are really suffering from erratic weather changes, unpredictability, and so forth. I was just organized and moderated a panel earlier on just transition in smallholder agriculture, and the common message for them was that we are either drowning in water or we have a drought. We have typhoons or we have stillness, so all the insects are eating all our crops. It's a huge problem. So I think it's so great that we're talking about this now, and particularly now in these next couple of weeks, a lot of the conversations around adaptation and the GGA, the Global Goal on Adaptation, and funding for that is going to be on the table. And I think what we're talking about here, and particularly looking to the past to find those solutions to adapt the food production, is going to be essential to that. Okay, so Ms. Euler, I would like to come to you first. Brazil is a country with a strong traditions in agriculture, but also as a country affected by climate change. As what would be your view on the use of genomic techniques in the future climate adaptation foods of systems of Brazil? So in other words, what is your stance on genomics to adapt to a changing climate in Brazil?
Okay, very close. Can you hear me? Yes. First of all, thank you very much for this invitation. President Silvia could not be here, but Embrapa is represented. Our partnership with Nordic is so special, important. I'd like to address the professor. I'm really touched with your passion. You really inspire us. And I would like just to share with you that we have, I was reflecting through your words, and we have a leadership that was a former constituent deputy. His name is Ailton Krenak, and currently he's the first indigenous people that is part of our National Academy of Letters, because he's a writer and a poet and also an environmentalist. So it's someone very important for us Brazilians. And he used to say that the future is ancestral. And you know, you just proved this to us. So this just brings to me one of the messages of the Paris Agreement that we should put and really understand that local knowledge, ancestral knowledge is as important as scientific knowledge, and it's our challenge. And I think that this COP represents a lot how we researchers, Western education, deal with this. So now going to your question, I will have to go aquí to come for some tips. So we believe that genomic techniques will play a central role in building the future climate adapted food system of Brazil. By the way, women, yesterday we had at the AgriZone one meeting of one women coalition for economic adaptation. And one of the numbers that really called my attention is that the whole funds, trillions of dollars yearly, less than 1% goes to adaptation. And that usually women are the ones that are really protagonists in the terrain of the adaptations. That's why we created at this COP one women coalition. So welcome to it. Coming back to my duty here, our country's strong agricultural traditions are now facing the challenges of changing climate, with rising temperature, prolonged droughts, and increasing pressure on soil fertility. To face this, science must work hand to hand with nature. That is exactly what Embrapa is doing through the Genomics for Climate Change Research Center, a joint initiative with the University of Campinas, Unicamp, and supported by FAPESP. At the intersection of genomics, biodiversity, and climate science, the GCCRC turns biological knowledge into agriculture innovation. Our researchers study genes, regulatory elements, and microbial organisms that help plants tolerate heat, drought, and nutrient limitations, all of which are becoming more frequent in tropical agriculture. What makes this work unique is that it connects cutting-edge genomic science with Brazil's extraordinary biodiversity, using native species from extreme environments and models for adaptation. For example, in the Brazilian Campus Silvestres, I guess we are talking about Caatinga, plants of the Velosia genus and their microbiomes are being studied to uncover genetic and microbial traits that allows survival in soil with very low nutrients and limited water. These native systems are not only ecological treasure, but also living laboratories that inspire new biotechnology solutions for resilient crops. At the same time, the center has built a strong technological platform for the genome editing and transformation of tropical maize lines, something that had long been a limitation since most protocols were developed for temperate varieties. By successfully applying CRISP-Cas9 to maize adapted to Brazilian conditions, our scientists opened new possibilities to develop crops that are more resistant to heat, drought, and poor soils, while maintaining productivity and nutritional quality. In a sense, genomics is giving us the tools to translate language of biodiversity into agriculture resilience. We are talking the same, right? It allows us to move beyond traditional breeding by directly identifying and applying the genetic and microbial assets that nature has evolved million years ago. Through initiatives like the Center, Embrapa demonstrate how science, collaboration, and open data can accelerate the transition towards sustainable, climate-ready agriculture. One that not only feeds people, but also preserves ecosystem and strengthens our national capacity to innovate. Thank you.
Muito obrigado e parabéns com a coalizão de mulher. Bem legal. That just makes me think while you were talking that one of the things when you always talk about innovation technology, something we have to be very mindful of is the precautionary principle. But I'm guessing looking to the past, what worked addresses that in a very novel way, which I find incredibly interesting. So from one massive research institution to another, Todd, you are the science director for climate action at CGIAR. And could you talk us to a little bit what happened recently in January? There was 150 Nobel and World Prize Foundation laureates. They called for a moonshot initiative to secure substantial leaps in food production for food and nutrition security. What kind of moonshots do you see as necessary in the coming years?
Wow.
Big question.
Yeah, big question. Just to take a little temperature in the room, how many of you know of the CGIAR?
Come on.
Hey, you should have seen the room I was in earlier. so that's great. I mean, sometimes people call us.
Who knows Embrapa?
Oh, come on.
Sorry.
Come on. You're stealing my thunder here. Come on. But yeah, so it's a great question, and one that we grapple with right now as we think towards the big innovations of what's coming up. But the really, I'm first ultimately inspired by your talk. Amazing job. But ultimately, as we're thinking about this in terms of genetic innovations, which is a key topic within the CGIAR, we're really thinking about what kind of assets do we first have ourselves. So CGIAR, as many or some of you may know, is the house of one of the largest gene bank repositories. We manage 10 gene banks, hundreds of thousands of accessions of many of the staple crops across all of the world. So we are a key resource for many of the types of science that new innovators are looking at every day. And so, for instance, even you were speaking about rice. Erie, along with partnerships and public-private partnerships with Google, has already sequenced more than 3,000 rice sessions. It has 120,000 more in planning. So these are key foundational assets that we just can't lose. And so the moonshot is actually getting all of this genetic material into open repositories, because we need this information to be publicly available to speed discovery, not only for companies, but also for national research institutions and national systems as well. And so CGIAR is committed to open and fair data for all of the gene banks. And so this is one of the key moonshots, as you would say. A second moonshot that we're working on quite a lot is around allele mining, which isn't necessarily a moonshot as a new technology, but it is a moonshot for how it can serve both adaptation and mitigation purposes. So with Novo Nordisk and other partners, we've been working on biological nitrogen inhibition. And so with BNI, or biological nitrification inhibition, essentially what you're doing is slowing down the nitrogen cycle. So we've targeted genes that are slow down the nitrogen cycle. That means reduced economic pressures for fertilizers. That means reduced nitrogen losses into the environment. And so we're seeing both economic benefits for farmers as well as environmental benefits for the rest of us. And then the last piece that I'll touch on only briefly is a moonshot that people don't think. Not all moonshots are about technologies. Oftentimes, it's just about getting things into the right pipelines. And so our moonshot is actually developing the breeding pipelines with national systems, which doesn't sound so much like a moonshot when you think about environmental DNA, perhaps. But in fact, these are critical bottlenecks to actually getting seeds into farmers' fields. And so we've set up product design teams in more than 25 countries that work with national systems to get this information and be able to propagate these advanced technologies into farmers' fields and make sure that not only the seeds, but then the actual scientific advances are owned by national systems. Thanks so much.
Thank you so much, Todd. And right on cue, talk about climate systems. The afternoon downpour has started. Please indicate if you cannot hear us for whatever reason. It doesn't sound so bad yet. So, Majal, coming to you. So when we talk about the Paris Agreement, talk about climate change, talk about multilateral conversations as we're having here, all of that has to be anchored in national roadmaps and national plans, in DCs, and also linked within BSAPs and so forth, but also very much integrated and put into work on the ground. So when you look at that, and based on what you've heard so far, how can we bridge the gap between some of the frontier research and the real world agriculture and innovation, ensuring that discoveries like those from AEGIS benefit farmers globally? How can we make sure we move beyond that? And particularly if you have any thoughts about R&D and IP and how we can take this amazing work and ensure it actually hits the farmers, and preferably soon, not in 20 years.
Okay, thanks, Lars, for the question. I will be brief. I will mention 3 points. So, how we translate, and by the way, I will not start...
in here, we can hear better.
Okay. And by the way, I will not start asking who knows FAO or the UN. Sorry, guys. No, but to be more serious, it's how to translate the science and the most advanced science into policy that will then be unfolded to reach the ground of the people. So, 3 points. You need policy instrument, policy environment. So, as you mentioned, some policy, or we have biodiversity policies, NBSAP, we have climate policy, nationally determined contribution, national adaptation plan, long-term low-emission development strategy. We have agriculture policies, simply, for the production. So for that, you need settings. So FAO is one. Biodiversity is part of FAO mandate. And for that, we have 2 bodies that are helpful. We have a Commission on Genetic Resources for Food and Agriculture, and we have the International Treaty on Plant and Genetic Resources. Those have 2 different mandates, but they're important because they're the one that will translate on the science into something that you can activate at policy level. A different aspect, the treaty and the commission can complement. One is more looking at the legal aspect, because you have also legal aspect. You were mentioning indigenous people, depending where you will find that. It has probably some patent right, or it's a public good. So you have to discuss that.
Benefit share.
Yeah, beneficiary. Yeah, cool. Will beneficiate from that discover. So this is the first point. The other point I want to make, and this really direct to part of your speech, this has been part of a systemic approach. You cannot just build on genetic. you have also to build on the practices, the farmer, how they will embed, because new plants, new traits mean new or different practices. So you need also to translate that, and it's a systemic approach you need to have. And you were mentioning something that is very interesting. We have to look at the past to see the future, but the future is not really, let's say, positive for the plant. If you look, there was a study recently published on 30 crops, and we embedded that in our tool to help policymakers to make decisions. On the 30 crops, 5 of them, I have the name here: wheat, coffee, beans, rice, cassava, plantain, which resonate, I guess, a lot also for Brazil. We will lose net loss of suitable area. Because yes, we move north, but the duration of the day is not the same as on the south. So what we will gain will never compensate what we are losing. So that's why we need not just to move, but to move and adapt and change the plants. So when you were mentioning that, I was creating that connection here. So we need the systemic approach, because new plants with new genetics mean also new ways to manage those plants. And the last point is connected to also manage. Who is managing? The farmers, the people. So they will need also to have some support, capacity building, a lot of capacity building. So we rely, I know that Embrapa and CGIAR, you are doing a lot, and you have a lot of science that is oriented towards the farmers. So this is basically what we have to activate, and to activate better. So this is how you manage to translate a science that can be seen by some policymakers, something like, oh my goodness, this is an article in Nature, I will not understand. There is a lot of GTCA, so the genetics, and for me, it does not resonate. But how we translate that into the policy, and then from the policy to the farmer. So those are important elements that I try to share with you here. Thank you for the question.
Thank you so much, Marjal. And I see His Excellency Jakob Jensen has arrived. We're going to come to you in just a few minutes. I just wanted to come back to the panel just for a lightning round of a few questions. Essentially, you talked about basic research we're discussing here today. You talk about the importance of using the research and implementing it into ongoing research, and you talk about the systemic frameworks we need. We cannot just talk about this innovation has to be anchored in a system. To do all that, we need funding, right? And all of these things are funded individually, but how do we make sure that this is funded both at a multinational level, the national level, and even the subnational level? What is needed? Is it mainly public funding? Do we need to look at blended finance, like public-private partnerships? Any thoughts, best way, particularly when we're talking about this kind of technology? Eske first.
Yeah, thank you very much. I mean, I think that you need at least some longer-term funding, right? I mean, you need some time to you can say do stuff, and then I think that both researchers and organizations, but also foundations, needs to work together in order to kind of, you can say, you explain kind of the chain, right? In order to get all the way into something useful, and we need of course to connect those different chains, right? So we are getting there, and that's what I hope, at least from my point, that this COP30, I mean, meeting you guys and talking to, learning, how is the ecosystem that we can start building the connections, right? So we can go from the research findings and all the way out there. And I just want to also mention, if I may, that I agree with everything you said. First of all, I just want to mention that we are, in fact, also working with indigenous peoples, right? So even in Brazil, we are working with on these Black Earth. Yeah, and together with researchers from São Paulo and also in native communities, right? And try to understand how are they formed, right? And of course, if anything comes out of it, we make sure that there's financial benefit sharing. So I'm all for what you're saying, and I'm also for what you're saying, that it's not enough to move things north. But what I think is important to say is that traits, for example, that you find which are adaptive, let's say, to a warm north, is of course also potentially very interesting to other environments, right? Because you're talking about a very fast flowering time. So that in principle could be interesting also for desert-like environments where you have, so it's not like only one, you can say a trait that you find in one system necessarily are only restricted to that system in terms of use.
Thank you so much, Eske. Just we're running slowly out of time, so maybe the rest of you can just take 30 seconds each just to some
Wow.
closing thoughts.
Let's go. I
Vamos.
want to come really to a real world. What's going on right now? We have one very we have a disease that appeared 2 years ago in the border between Brazil and French Guiana, that came from the Asia and had the first occurrence in the border, and it's named, the popular name is cassava witch disease. And the cassava is the basic food, daily food for Amazonians and for Brazilians in general. Even myself in Rio, I eat farofa a lot that's made by cassava, okay? And we are the center of diversity of cassava. And really quickly, inside the indigenous territories, this disease devastated all production and all varieties. So the first fund that we could mobilize, two funds we could mobilize very quickly. One was the CGIR, and we are working on genomics, so looking to the future. And other one, very small fund, $200,000 from the Ministry of Agrarian Development, that could help us to do the research with the indigenous people, asking them permission, explaining everything, and asking if they would like us, Embrapa, to introduce our cultivars there. And we did it. We have the greatest, probably, CGIR will tell me if I'm true, but the greatest manioc gene bank in the world. But even though Embrapa do not have the solution. And after 2 years, and only with $200,000, because it's so difficult to mobilize funds for that, we found out that the solution is inside of the territory. They have the varieties when they make the shift and burn and plant new cassavas by the seeds. So, but my final statement, how to do it, the most important thing is to strengthen governance, because it took us 2 years to really to put the Ministry of Agrarian Development, along with the Ministry of Agriculture, along with the state government, because we started in one municipality. After 1 year, 18 municipalities already spread. So I think the big challenge is to put everybody on the table and to say this is priority, and let's try to get one agreement. Let's try to have trust among all of us. And then, but anyway, it's still not enough. We have to do much more. But after really investing our time in strengthening governance, the answers came quicker. Thank you.
Thank you so much, Anna. And Todd, over to you, just maybe briefly, 15 seconds.
15 seconds. We need to access all sources of funding, because some of these are public goods that will not be funded by the private sector. Some of these have risk thresholds and need such innovative science that will not be funded by the traditional private sector. And so we need to find the coalition of the willing to fund all of these in a consortium.
Maja?
I will be even shorter, because I will make mine those words on saying how we do that. We need to create partnership to discuss the access to finance and to discuss the quality and quantity of finance. So just mentioning that since several years we have implemented the food and agriculture process level transformation. We will put around the table, and in the board we have CGIAR, we have the farm organization, and we have the banks, and the public national development banks, and the government. And this is reflecting on how we make the finance for agriculture more accessible, or we turn agriculture also more attractive to investment. So that's it.
Thank you so much, Majal. Please give a round of applause to our panelists here. You may go down and have a seat. And Mr. Jakob Jensen, if you would please join me on stage. There's a... You can stand wherever you want. So, ladies and gentlemen, this is Mr. Jakob Jensen. He's the Minister of Food, Agriculture and Fisheries for Denmark. And Jakob, we've heard now a little bit how you take a microscope, look into the past to help be realistic about planting and growing food in the future. We heard the importance of governance, technology, heard the importance of integrating on the ground and ensuring that indigenous communities, smallholder farmers are involved from the beginning. We heard that it has to be in a systemic approach, not just the technology has to be systemically introduced across the food system, and it has to be used in a way that we can find funding for it, whether that is public funded, blending finance, in a way so we can actually take it forward. And particularly in the context where we are now, we think the adaptation conversations are important. Your thoughts for a few minutes on that.
This is working? Yeah, now it's working very good. Thank you very much. Sorry I came a little bit late. That was due to some royal obligations, but we'll get back to that later. But thank you so much all for coming here today. It is definitely a true honor for me also to give some concluding remarks on this very, very important event. Thank you, Professor Willerslev, for joining us, and also to the distinguished panel that we heard before, to providing some inspirational thoughts and reflections on the role that ancient DNA in our future cropping system. Today, unfortunately, you could say 700 million people are food insecure and desperately poor. And about half that number, they don't know where their next meal is coming from. These numbers are hard to understand and as hard to accept. Unfortunately, we are headed towards a future which is even more food insecure. So in other words, food production must increase among 60% to secure food security for the predicted population in the year of 2050. And this is a real challenge to all of us, worsened by unstable worlds with wars and conflicts, with deepens food insecurity even further, and worsened by the climate change we can hear just now outside, that will also decrease the productivity for most major staples when sustainable increases are needed to feed the world. For maize, the major staple for much of Africa, decreasing yield is projected for virtually its entire growing area. Increasingly common extreme weather events associated with climate change will only make these things even worse. So, in other words, we need to find some solutions for the future of the global cropping system. Earlier this year, more than 150 Nobel and World Food Prize laureates called for a so-called moonshoot, efforts to sustainable leaps in food production and food nutrition security. And their main message to the world was that today's challenge of access to food will be worsened by production challenges of tomorrow. So we are not on track to meet future needs, not even close. However, there is hope. There is hope. And today's event symbolizes that hope for the future. And I believe that research and innovation is the key. So we need to support innovation in agriculture to realize these moonshots efforts. From an EU perspective, Denmark supports work on new genomic techniques. This offers a major opportunity to make farming more sustainable and more resilient. It can deliver crops that use fewer inputs, withstand climate stress, and provide better nutrition. And at the same time, it allows plant breeding to happen much faster than today while maintaining a high level of safety at the same time. So all that being said, from my side, thank you very much for coming here today, and I hope that you have had some inspiring words from Professor Willerslev and the distinguished panel that we saw just before. Thank you all, and good luck with the work from here. Thank you so much.
Thank you so much, Your Excellency. And I'm sure most of you who are not familiar with his work are eager to learn more. And if you want the easy way, just Google Eske Willerslev, and a lot of information is going to come up. And of course, feel free to mingle with the other attendees here. Thank you so much for coming. Thank you so much for staying longer. Really appreciate it. Have a good day.